It entered quietly, as most revelations do, not with the thunder of celestial drama, but with the stillness of something that had drifted through interstellar night for ages beyond memory. 3. Atlas approached the solar system like a wandering thought crossing the threshold of consciousness, its motion almost too soft, too smooth for the violent mechanics that normally govern cosmic debris. There was no warning, no luminous prelude announcing its presence. Instead, telescopes caught a faint pulse against the velvet dark, a point of reflected sunlight moving with the determination of an object that had journeyed far beyond the familiar gradients of our sun's gravitational reach. Its trajectory traced a line that was neither hurried nor hesitant. It slipped between the planets like a shadow brushing the edges of a dream, carrying with it the glint of metals, the whisper of ancient ice, and the faint spectre of a shape not easily categorized. To the astronomers who first noted its presence, 3I Atlas seemed unremarkable, at a glance a second interstellar visitor, following in the path left by 1I Oumuamua and 2I Borisov, joining the small and escalating family of objects arriving from the galaxy beyond. Yet even in those earliest frames, long before the strange jets or the confounding rotation numbers were known, there was something about its light that made some observers pause, a slight asymmetry. A glimmer of polarization that felt too polished, too deliberate. Space is a forge of endless collisions. Comets are shaped by heat and shattering, asteroids chipped by uncountable impacts, dust sculpted by stellar winds. But 3I Atlas reflected light with a quiet smoothness, as if its surface had been allowed to rest undisturbed by cosmic violence. It navigated the darkness not like a remnant of destruction, but like a fragment of a forgotten order. The solar system turned its indifferent face toward this intruder, but the intrusion did not feel accidental. There is a certain rhythm to objects that belong to a star system born of its debris, pulled by its gravity, annealed by its heat. Their paths are predictable, circular or elliptical echoes of the system's own long history. But 3I Atlas was a visitor, a messenger from a place without a name, carrying within its structure a record written by distances we have never touched and physical conditions we can scarcely model. As it glided closer, photons bounced from its surface and traveled millions of kilometers, reaching the mirrors of telescopes perched on mountaintops and orbiting far above clouds. Each captured ray offered a clue, though at first the clues seemed almost insignificant. Its brightness curve flickered in a way that did not quite match the spin signatures of known comets. Its color sat at an intersection of metallic hues and dusty reds seldom seen in a single body. Its approach vector aligned, by mere chance or by the quiet design of cosmic geometry, with the same patch of sky that had once delivered a brief, unrepeatable radio signal in 1977, a coincidence that would later haunt the narrative surrounding the object. But none of this was enough to provoke alarm. The universe is vast, and strangeness is its native language. Astronomers catalogued it, traced its orbit, noted its likely origin in the distant outskirts of a dying star, or the collapsed remains of a planetary system long since silenced. They prepared to file 3I Atlas among the growing set of interstellar travelers passing through our celestial neighborhood. What they did not know, what no one yet imagined, was that this quiet arrival marked the beginning of a sequence of discoveries that would steadily erode the foundation of cometary physics. Within months, the object would reveal jets that behaved like lines drawn with a ruler against the void. Its rotational data would unfold into a paradox so complete that equations older than modern astronomy would buckle under its implications. Its composition would whisper of metals in proportions that felt alien to the architecture of familiar comets. and the silence surrounding its first images would bloom into a chorus of impossible measurements. But in this earliest moment, none of that yet existed. There was only the object drifting inward, trailing behind it a wake of interstellar dust too faint to see. The planets continued their ancient orbits, the stars shimmered in their distant, indifferent brilliance, and 3i Atlas moved quietly across the sky, a solitary traveler carrying an internal logic that the solar system had never before encountered. Even then, the mystery had already begun subtle, unfelt, unfolding in the patient way the universe reveals truths it has carried for aeons. For every object that enters the inner solar system, the sun becomes a lantern, illuminating its flaws, its fractures, its icy cores. But as the sunlight touched the surface of 3i Atlas, it did not evaporate into familiar plumes, it did not split into chaotic sprays. Instead, something slept beneath its exterior, waiting for the right angle of illumination, the right distance from the sun, the right moment to declare itself. The early images were simple, a faint smear of reflected light, a wandering dot among background stars. But they carried with them the quiet foreshadowing of upheaval. The telescopes that captured them had no way of knowing that this unassuming object held within its motion a contradiction, one that would later force scientists to ask whether the laws they trusted were complete, or whether the cosmos had been hiding a more intricate architecture all along. For now, 3i Atlas was simply approaching, gentle and unhurried. Yet in its silence, there was a gravity not measured by mass, but by mystery, an unspoken weight that would soon pull astronomers, physicists and dreamers toward a single, unsettling question. What, exactly, had entered the solar system this time? The earliest glimpses of 3i Atlas were not accompanied by alarms or proclamations. They came instead through a mosaic of small observations, specks of data scattered across observatories in Hawaii, Chile, Spain, and the Canary Islands. Each telescope captured its own brief encounter with the visitor, stitching together the first faint outline of what would become one of the most perplexing interstellar mysteries of the modern era. Astronomers, accustomed to the quiet rhythm of comet tracking, logged the object almost automatically. Another dim point, another orbital track to refine, another catalogue entry waiting to be assigned. It was during these initial days that the rotation measurements began. At first, they were routine, a periodic fluctuation in brightness, the telltale pulse of an uneven surface spinning in sunlight. Objects tumbling through space tend to brighten and dim as their geometry changes orientation relative to observers, a predictable signature that allows scientists to infer rotational speed. For 3i Atlas, those measurements soon converged with remarkable consistency. 7 telescopes, observing independently between late July and early August, reported the same value, a rotation period of 16.16 hours. Not 16, not 17, not a range or a noisy cluster of approximations, but a clean, elegant number measured almost identically across nights and continents. In the moment, nothing about that figure seemed remarkable. Comets often rotate with periods anywhere from hours to days. A spin every 16 hours placed 3i Atlas comfortably in the middle of known behavior. And yet, even then, an undercurrent of curiosity threaded through the data. The object's light curve exhibited a subtle regularity less chaotic than typical comets, more reminiscent of a body whose surface features were strangely uniform. But astronomers have learned not to overinterpret such impressions. The cosmos is full of optical illusions, shadows masquerading as certainty, so the number was recorded, confirmed, and set aside. Through autumn, the object drifted deeper into solar illumination. More telescopes were turned toward it. The light curves remained consistent. The rotational speed showed no sign of acceleration or decay. Everything about the visitor's motion suggested a stable, coherent body, an interstellar rock untouched by catastrophic fragmentation. In essence, 3I Atlas behaved exactly as a comet should. But the images captured in early November contradicted that simplicity with a violence no one expected. A new set of observations from ground-based telescopes and from several institutions coordinating their nightly watch revealed long, luminous jets unfurling from the object. Not fuzzy, curling tails like those of typical comets, but straight beams of material, narrow and unwavering. These structures extended for millions of kilometers, yet maintained an almost impossible precision. In the frames taken on November 9th, the jets stretched outward like the beam of a lighthouse slicing through darkness. To astronomers familiar with cometary outgassing, the sight was immediately perplexing. Comets rarely produce jets so coherent. Their tails, sculpted by rotation and solar radiation, tend to blur and twist. But here, in the raw data, were columns of expelled gas that looked as if they had been drawn deliberately. Only days earlier, images captured of the same object had shown nothing, no jets, no plumes, not even a faint dust coma. Its surface had been silent, its behavior subdued. Something had changed, abruptly and dramatically, and no one yet understood why. The early November images triggered a flurry of recalculations. If the jets were real, and every telescope agreed they were, then they demanded an explanation that matched both the observed gas velocities and the object's rotation. Astronomers returned to the rotation rate data gathered in July and August. They reprocessed the light curves, checked the signal-to-noise ratios, scrutinized each periodic oscillation. Had the numbers been wrong? Had something been missed? But the measurements remained firm. 16.16 hours, a result obtained independently, repeatedly, confidently. That figure became the fulcrum around which the unfolding mystery turned. For if 3I Atlas rotated every 16 hours, then the jets shouldn't look like this, not sharp, not constant, not unwavering over millions of kilometers. They should have smeared into spiraling ribbons as the object spun, each plume becoming a twisted helix in space. Yet nothing of the sort appeared in the images. Instead, the jet stood still. The realization dawned slowly, spreading through the astronomical community not as a sudden revelation but as a creeping tension. Something about this interstellar visitor did not conform to known behavior. The jets, the rotation, the timing, it all hinted at a deeper inconsistency, one that was only beginning to take shape. What the early observers did not yet know was that 3I Atlas was not merely rotating and outgassing simultaneously. It was performing these motions in a way that seemed to disregard the rotational impact entirely. It expelled material that behaved as if the object were motionless, even though it was spinning 45 times over the month-long travel time needed for the gas to reach the outer edges of the jets. That contradiction would soon become the center of international discussions, driving teams to revisit the earliest data, searching for any faint clue that might have predicted the anomaly. But nothing in those first glimpses had spoken clearly enough. The object had slipped into the solar system delicately, shadowed by the quiet indifference of distant starlight, giving astronomers no reason to foresee the physics-breaking narrative it would eventually impose. Only in hindsight would those earliest observations seem ominous. The smoothness of the light curve, the precision of the rotation rate, the calm surface, the silence before the jets. Astronomy is full of moments that feel ordinary until the universe reveals their significance. And so it was with the first glimpses of 3I Atlas. They were the opening strokes of a mystery that would grow beyond the edges of established science, a puzzle waiting to unfold its deeper layers as the object moved closer to the sun, revealing more of its strange internal geometry. For now, the data merely sat in archives, waiting, complex, precise, deceptively ordinary. The calm before the revelations to come. The moment when the numbers broke did not arrive with fanfare or dramatic announcement. Instead, it appeared quietly, hidden in the margins of a spreadsheet, an inconsistency so stark, so mathematically absolute, that the researchers who first noticed it assumed they had made a simple mistake, a misalignment in the timestamp, a calibration error in a telescope's CCD array, a misread parameter in the rotational model, something trivial, surely, something human. But the inconsistency refused to disappear. The paradox emerged when scientists overlaid two types of measurements taken months apart, the rotation rate of 3I, Atlas, and the newfound jets captured in early November. Each dataset, considered alone, behaved exactly as expected. Together, they formed an impossibility. The rotation period, 16.16 hours, was rock solid. 7 independent observatories had measured it. No variation, no drift. No signs of torques, impacts, or outgassing-induced acceleration that could alter its spin. It was one of the most precise rotational measurements of any interstellar object ever recorded. Then came the jets, 3 beams of material extending for millions of kilometers, each one straight as an arrow, unbent by motion, unblurred by rotation. This is where classical physics intervenes. When a spinning object ejects material, the expelled gas should retain its initial direction at the moment of release. Meanwhile, the object continues to rotate beneath it. The result, predictable, inevitable, is a spiraling spray, not a straight line, never a straight line. The math is elementary. If the gas takes roughly 1 month to travel from the object's surface to the visible tips of the jets, then during that month 3I Atlas completes approximately 45 full rotations, enough to twist any jet into a swirling corkscrew spanning the length of its journey, enough to paint the sky with the signature of motion. But the images show no corkscrews, no spirals, no discernible curvature, only linear precision, as if the jets were frozen in place, ignoring the frantic spinning of their source. This is the moment scientists struggled to accept. The physics involved was not exotic or speculative. It was the same Newtonian mechanics that govern rotating sprinklers, spinning asteroids, and the simple paths of particles moving in a vacuum. A rotating body cannot produce linear jets over tens of millions of kilometers unless something profoundly unusual is happening. For the first time, 3I Atlas broke the trust scientists' place in the natural order of things. The data forced a chilling realization: either the jets were not responding to rotation, or the object was no longer rotating the way earlier observations indicated. Both possibilities were deeply problematic. If the jets were somehow unaffected by rotation, that implied a mechanism capable of maintaining a fixed orientation in space, despite the object's spin, an idea incompatible with natural cometary physics. If the rotation had somehow slowed or ceased entirely in the months between measurements, then some immense physical perturbation must have occurred, something catastrophic enough to strip angular momentum from a multi-hundred-meter body. Such catastrophic events leave debris fields, fractures, thermal signatures. None appeared in any observations. Thus, the contradiction remained naked and defiant. The numbers refused to reconcile. In scientific circles, contradictions are the seeds of revolution. They are the quiet detonations that precede paradigm shifts. Yet, before a revolution can begin, denial must run its course. Researchers ask themselves what they always ask when the universe behaves strangely: what did we misunderstand? Theories were drafted in haste. Perhaps the rotation had been misread. Perhaps the jets had been mismeasured. Perhaps the gas dynamics were being influenced by unseen forces, solar-wind interactions, plasma environments, or unusual surface geometries. But none of these explanations held. As additional images arrived, the straight-line jets appeared again, unwavering and unbroken, as if drawn by a hand that refused to acknowledge the object's rotation. They shone like cosmic lances, narrow, unflinching, anchored in a direction independent of the body that birthed them. The tension grew quietly. In laboratories and observatories, researchers stared at the data and felt their confidence shift. The universe is not obligated to preserve human expectation, but it seldom violates the fundamentals so cleanly, so publicly. The contradiction at the heart of the three I-Atlas jets threatened more than a single model. It undermined decades of understanding about how solids, gases, and angular momentum behave in vacuum. Even more unsettling was the way the anomaly interacted with everything else known about the object. Its low water content, its high nickel concentration, its unusual polarization, its uncanny arrival direction. Each of these details had once been strange but manageable, each requiring only small adjustments to existing theories. But the jet paradox was not small, it was not marginal, it was not a subtle misalignment. It was a collision between observation and the very equations that describe motion. And collisions of this magnitude are rare. Scientists often speak of cracks in the model, small fractures that hint at underlying mysteries. But the paradox of 3I Atlas was not a crack. It was a fault line, clean and deep. It demanded new physics, or a new interpretation of familiar physics. Something about this object moved beyond the boundary of what natural bodies do. In meetings, researchers debated the implications with an unease they rarely voiced. Was this simply an interstellar object, with properties shaped by conditions alien to the solar system? Or was something deeper at work, something intentional, something engineered, something aligned with the kind of directional control exhibited by propulsion systems rather than sublimation jets? No one was ready to say so publicly, not yet. But the numbers had spoken. Reality had diverged from expectation, and the scientific community found itself staring at a mystery that seemed to whisper that the universe still held secrets capable of toppling even its most trusted principles. Something about 3I Atlas was wrong in a way that felt deliberate, as though the object's behavior had been sculpted rather than sculpted by chance. And with each new observation, the tension between what should be and what was grew sharper, colder, more undeniable. 3I Atlas had broken the math. And once the math breaks, the world can never return to what it was before. As more telescopes turned toward 3I Atlas, the unfolding narrative began to resemble a slow, methodical excavation, each new layer of data revealing something stranger beneath it. What had begun as an ordinary interstellar visitor was now unraveling into a tapestry of contradictions. The deeper scientists probed, the more the object resisted interpretation, like a piece of machinery whose internal design refused to match any blueprint known to nature. The turning point emerged when researchers began aligning the sequences of observations across multiple months. July and August had provided the critical rotation measurements, 16.16 hours, stable, precise, confirmed repeatedly across 7 separate facilities. Those values should have governed everything that followed. Rotation is not an optional characteristic, it is a mechanical heartbeat, and whatever jets or structures appeared later would have been shaped by that unchanging rhythm. But the November images ruptured the continuity. On November 9th, 3I Atlas revealed its first monumental anomaly, the straight-edged jets that refused to spiral. Millions of kilometers long, narrow as blades, Their geometry remained indifferent to the 45 rotations the object should have completed while the gases expanded outward. Earlier, from November 5th to 7th, the object had shown no jets at all, only a faint, inert form gliding against the star field. There had been no transition, no gradual increase, no intermediate plumes. Just stillness, then precision. A month-spanning mystery had taken root. To trace its origin, scientists began reconstructing the timeline with forensic care. The July-August rotation measurements became the foundation. Researchers revisited the brightness variations captured across those weeks, confirming that the periodicity was not an artifact of observational cadence. Every pass through the light curve displayed the same amplitude, the same rhythm, the same steady spin. Then came the September and October, data scant but important. A handful of observatories had kept the object in their nightly routines, capturing intermittent images as weather and scheduling permitted. These early autumn images showed nothing unusual. No jets, no thermal signatures, no deviations in brightness, fluctuations that would hint at rotational change or surface disruptions. By late October, the object was approaching the threshold at which solar heating could trigger outgassing. And yet even then, in the final days before the jets appeared, 3I Atlas remained dormant. This was the first fracture in the expected sequence. Comets typically begin responding to sunlight gradually, their jets strengthening as volatiles warm and escape. But 3I Atlas moved from absolute silence to fully formed, fixed-direction jets with no observable buildup. It was as if the object had been waiting. And then, on November 9th, the anomaly surfaced fully, captured independently by ground-based telescopes across multiple continents. Each image showed the same impossible morphology: straight, collimated, undisturbed by rotation. The beams seemed anchored not to the object's surface orientation but to some unchanging external reference, as though locked to a spatial direction independent of spin. This raised the unavoidable question: could the rotation rate itself have changed between August and November? Scientists tested this hypothesis ruthlessly. For the jets to remain straight, the rotational period would have needed to slow dramatically, falling from 16 hours to something approaching days or even weeks. Such a deceleration, however, would require an immense torque, far beyond what natural cometary processes could generate. Sublimation accelerates rotation, it does not dampen it. Collisions that could alter spin leave debris. Catastrophic breakups leave thermal signatures. None appeared. In fact, a set of images from November 11th, only 2 days after the jet anomaly first appeared, showed the object intact and thermally stable. There were no fractures, no dust clouds, no evidence of structural collapse. The body behaved as if nothing unusual had occurred, even though the physics of its jets refuted that assumption entirely. This dissonance forced astronomers to re-examine the rotational data from November itself. More light curves were taken, more photometry performed. But the object's orientation remained frustratingly ambiguous, partly because its jets outshone surface irregularities, and partly because the jet's directional rigidity masked rotational signatures usually found in cometary coma patterns. The deeper scientists dug, the clearer it became. The contradiction did not emerge from poor measurement, it emerged from the object itself. July and August told one story. November told another. The bridge between them was missing. The timeline reconstruction highlighted a blank space, a window in which something profound must have occurred, yet left no detectable trace. This absence of transitional data became its own form of evidence. If the rotation did not change, then the jets must have. And if the jets remained constant despite rotation, then something was overriding the natural rotational influence. This realization created a cascade of uneasy implications. fixed-direction jets suggested a coordination more consistent with controlled emission than with passive sublimation. Each possible natural explanation required assumptions increasingly incompatible with physics. Perfectly shielded volatiles, mountain-induced shadowing that somehow produced continuous jets rather than pulsed ones, or debris trails masquerading as jets despite the intact nature of the object. Non-fit. The deeper the scientific community attempted to integrate the timeline, the more it resembled a puzzle missing critical pieces. July and August were clear. September and October were silent. Early November was anomalous. Mid-November confirmed stability without explanation. Like a coded message delivered in fragments, the observational record formed a structure that resisted conventional interpretation. The object was behaving with an internal logic that was not synchronized with the rotational rhythm measured months earlier. This mismatch, the point where the timeline failed to align, became the pivot on which the entire mystery turned. It was not just that 3I Atlas broke a rule of physics. It was that it did so in a way that suggested deliberateness, as though the jet's behavior followed an unchanging reference frame, unseen by the rotation of the body itself. Science advances by finding such fractures. And in the deepening analysis of 3I Atlas, the fracture widened into a cavernous question. What keeps a jet fixed while the world beneath it spins? The deeper scientists pushed into the mystery of 3I Atlas, the more the entire paradox narrowed onto a single unyielding fulcrum, the month-long journey of its expelled material. This lone temporal fact, 30 days of outward travel, became both a map and a mirror, reflecting the strange physics at work inside the interstellar object. It was a timescale simple enough for any orbital mechanics student to calculate, yet devastating enough to destabilize the foundation of cometary science. When astronomers first measured the velocities of the jets, those luminous beams extending across millions of kilometers, they calculated the time needed for the gas to traverse the observed lengths. The answer, confirmed repeatedly, hovered at roughly 1 month, 30 days from surface to tip. It was an ordinary span for cometary outflow in a vacuum, unimpeded by friction, shaped only by solar radiation pressure and inertial momentum. In most circumstances, those 30 days would form the backdrop of a predictable narrative, the slow expansion of a tail, the gradual spiraling of material, the soft arcs that trace a comet's rotation like brushstrokes along the void. But here, predictability collapsed. The object's rotation period, 16.16 hours, meant that across those 30 days, 3I Atlas would complete roughly 45 full rotations. Each rotation should have imprinted its motion onto the jets, twisting them into spiraled ribbons. The gas leaving the surface should have spread outward at slightly different angles depending on the rotational phase at the moment of ejection. A natural jet emerging from a spinning comet becomes, inevitably, a curved structure. Not an artistic curve, not a gentle arc, but a severe, measurable curvature that grows more pronounced with distance. The mathematics woven through this expectation is as simple as it is unavoidable. Motion in a vacuum preserves direction unless acted upon by external forces. A comet's rotation is precisely such a force. Its jets, streams of sublimating volatiles, should behave like water falling from a rotating sprinkler, each droplet following a tangent path that diverges as the source rotates beneath it. Nature does not bypass these principles. There is no mechanism in classical comet activity that allows gas to ignore rotational motion. The object spins, the jets must curve. And yet, the jets of 3I Atlas remained straight. Scientists returned again and again to the 1-month travel time, 30 days, 45 rotations, millions of kilometers. The numbers formed a triangle that refused to close. Every calculation that expanded one side of the equation sharpened the contradiction in another. No possible balance could be achieved without discarding one of the three pillars. 1. The rotational period measured in July and August. 2. The jet lengths measured in November. 3. The straight, unwavering geometry of those jets. Remove any one of these, and the mystery dissolves into natural explanation. But none could be removed. The rotation period was confirmed by 7 telescopes, each measuring the same brightness modulation over weeks. The jet's travel time was constrained by well-established dynamics and by the object's known velocity. And the straightness of the jets was not subjective. It was photographic, geometric, undeniable. What, then, could preserve linearity across 45 rotations? This question became the epicenter of the scientific crisis. Several hypotheses, each more fragile than the last, were drafted. Could the jets be emerging from only one hemisphere? Yes, but the object still rotated. Could the body's surface contain deep pits shadowing the jets? Yes, but pulsed emission would create discrete bursts, not continuous lines. Could synchronous erosion somehow match the rotation? No physics affords no such mechanism. The month-long journey of the gas was the key that kept unlocking deeper impossibilities. During 30 days of travel, solar radiation pressure should have subtly widened the jets. The object's rotation should have imposed a helical pattern. Microgravity interactions should have diffused the gases. Thermal fluctuations should have modulated their density. None of this appeared in the November images. Instead, the jets resembled the light trails of something held perfectly steady, something maintaining alignment with a fixed orientation, not with the surface beneath it. This implication was uncomfortable. For the jets to remain straight, their direction would need to be controlled in a way that preserved a stable spatial orientation over weeks. Not merely aligned at the moment of ejection, but continuously corrected against the object's rotation. It would require a mechanism capable of sensing orientation, adjusting trajectory, and maintaining thrust direction independent of spin. Such control does not exist in natural comet physics. As researchers examined the models again, the object's rotation became less a characteristic and more an antagonist, an expected interference that the jets ignored. Its spin was not shaping the outflow. It was being bypassed. The only analogy that fit came not from astronomy, but from engineering. Spacecraft thrusters remain fixed relative to inertial space, not to the vehicle's rotation. A rotating probe can fire its jets to maintain a course, its system correcting for spin so that thrust remains globally aligned. Even if the craft tumbles, the orientation of the thrust vector remains deliberate. To see such behavior in a freely rotating object, one with no visible external structure and no detectable debris, was unnerving. The month-long travel time thus became more than a physical parameter. It became evidence of something operating beyond passive sublimation, something maintaining consistency over weeks, something aware, in a mechanical or structural sense, of its orientation in space. The implications reached far beyond comet science. They extended into questions of internal geometry, of controlled emission, of design versus natural formation, but the scientific community was not yet ready to entertain such interpretations openly. The data, however, made silence increasingly difficult. Because in the cold arithmetic of the cosmos, a straight jet across a month of rotation is not simply unlikely. It is forbidden. The numbers had aligned into a portrait that no classical comet could paint, and the longer scientists stared at that portrait, the more the universe seemed to whisper that they were witnessing something unprecedented, something that followed a calculus older than the solar system, shaped by rules the human species had only just begun to glimpse. The deeper one descends into the physics of 3I Atlas, the more the problem begins to resemble a quiet betrayal, an object turning against the very rules that should govern it. In comet science, nothing is more fundamental than the relationship between sunlight, ice, rotation, and the release of gas. These forces shape every natural visitor from the outer darkness. They dictate how comets brighten, how their jets twist, how their tails form, and how their surfaces fracture. These rules are so consistent that entire branches of astronomy rely on them to classify and predict behavior. But with 3I Atlas, those familiar rules began to collapse, one after another, until even the most conservative physicists admitted privately that the object was operating under conditions that classical models could no longer explain. The contradiction was not subtle. It was pure, cold, unequivocal. If the jets were produced by sublimating ice, if solar heating triggered the release of volatiles, then the rotation of the object must influence the direction of the jets. There is no alternative within established physics. Rotation is not a negotiable factor. It is a geometric consequence of motion. A spinning nucleus spraying gas behaves like a moving nozzle, tracing widening arcs as the ejection point sweeps around the axis of rotation. It cannot hold a jet straight. It cannot produce a collimated beam that ignores angular momentum. The universe does not make exceptions. And yet the images of 3I Atlas forced that exception. The frozen physics problem, the point at which natural law ceased to apply, arose because the jets behaved as though the object were not rotating at all. The jets appeared anchored to a fixed direction, as if drawn from a structure that remained oriented in inertial space, while the bulk of the body spun beneath it. This is impossible for a natural cometary nucleus. To achieve such stability, a mechanism would need to actively compensate for rotation, applying corrections at a scale measured in degrees per hour. The precision displayed in those beams, stretching across millions of kilometers without curvature, was mathematical in its discipline. The problem grew more unsettling when researchers revisited the timing of the jets themselves. The images taken only days before November 9th showed nothing, no outgassing, no coma, no hint of activation. For a natural object, sublimation begins gradually, initiated by the softening of volatile-rich layers as sunlight penetrates the surface. Jets begin weak, then strengthen. There is always a transitional phase, a ramp-up period, but 3I Atlas bypassed that sequence entirely. It shifted from silence to fully developed, impossibly straight jets in a single leap, as though a switch had been thrown. Such behavior introduced the second fracture in classical cometary physics, the absence of intermediate states. A natural process evolves, a controlled process activates. The failure of the physics deepened further when researchers examined the spectral behavior of the jets. Although full compositional data had not yet arrived, preliminary measurements suggested velocities inconsistent with typical sublimation-driven jets. Standard comet jets accelerate gradually, shaped by surface temperature and molecular escape velocities. But initial velocity estimates for 3I Atlas hinted at a magnitude and consistency that did not match solar heating, at least not in the uniform, unwavering way displayed in the images. As researchers modeled the forces required to maintain such linearity over millions of kilometers, they discovered something even more disturbing. For the jets to remain as straight as observed, the initial direction of ejection would need to be held stable to within fractions of a degree across the entire rotation cycle. Even a slight wobble would manifest as curvature in the jet, but there was none. The jets were not merely straight, they were precisely straight, as though oriented with something like gyroscopic stability. This implied a deeper impossibility, an internal stabilizing mechanism. Natural bodies do not possess gyroscopes, they do not possess control systems. They do not coordinate outgassing through mechanisms that sense and correct misalignment, and yet the gas flowed as though from a device engineered to resist rotational influence entirely. The more scientists attempted to force natural explanations into this puzzle, the more the puzzle resisted them. Every hypothesis led back to the same forbidden conclusion. The jets were behaving as if they were deliberately oriented. One of the most troubling aspects of the anomaly was the consistency of the jet brightness along their entire length. Natural jets diffuse quickly. Gas expands, density decreases, sunlight scatters differently along the trajectory, and particles diverge. But the jets of 3I Atlas displayed an uncanny uniformity, their structure maintained across distances where natural outgassing should have blurred into faint haze. If the jets were powered by solar heating, then the composition of the released material should follow the typical gradient of dust to ice ratios seen in comets. But the brightness profile here did not resemble dust-heavy jets. It resembled something closer to a focused stream of vapor or ionized particles, behaving with a consistency rarely, if ever, observed. The frozen physics problem deepened further when researchers considered the object's mass. Based on brightness and estimated albedo, 3I Atlas appeared too small to sustain jets of the magnitude observed for an entire month. The mass loss rate required to produce such beams should have significantly altered the object's rotation, but no such change was detected. Rotation remained unchanged from the earlier measurements, a contradiction that compounded the already fragile theoretical framework surrounding the object. A paradox emerged. The jets were strong enough to be visible across millions of kilometers, yet somehow too weak to alter the object's spin. This was the point at which many scientists quietly recognized that they were confronting something unprecedented. The laws governing momentum exchange, conservation of angular momentum, sublimation dynamics, all of them were being violated simultaneously in a configuration that pointed toward a deeper, unified contradiction. It was not one anomaly. It was a constellation of anomalies, aligned perfectly around a single object. Something about 3I Atlas was not obeying the rules of natural formation. Something was maintaining stability where none should exist. Something was shaping the jets with a precision mixed, not with randomness and chaos, but with coherent, sustained orientation. The universe is fluid, but its laws are consistent. When an object breaks them, the cosmos does not bend. It waits for humans to understand the breach. 3I Atlas had pierced the threshold where classical physics ends not through violence, not through spectacle, but through elegance, through alignment, through a refusal to behave like anything born of ice, dust, and the long memory of stars. It had become the first interstellar visitor whose silence was not emptiness, but tension, a set of physical contradictions coiled tightly together, waiting to be unraveled. As astronomers struggled to reconcile the straight, unwavering jets of 3I Atlas with the natural behavior of sublimating volatiles, a wave of theoretical improvisations swept through the scientific community. Each attempt to restore physics to its rightful place pushed the conversation deeper into speculation, not because scientists wished to abandon the familiar laws, but because the object forced them to confront possibilities that lay beyond the structures of known comet activity. Among the most discussed hypotheses was the terrain shadowing model, the vision of a landscape carved into extreme geological features, deep chasms and towering ridges capable of shielding pockets of ice from sunlight for most of the object's rotation. In this scenario, the surface of 3I Atlas would resemble a world of high cliffs and cavernous recesses, where volatile reservoirs sit buried at the bottom of shadowed valleys. As the object spins, the sun would periodically dip into alignment with these cavities, illuminating them for just moments each cycle. During these intervals, the buried ices would flare to life, erupting in jets of gas that burst from the dark, like geysers ignited by the touch of a distant star. Then, as the rotation continues, the geometry shifts, shadows return, and the jets fall silent until the next alignment. This idea had an aesthetic elegance. It could, in theory, explain intermittent emissions while allowing the jets to point in roughly fixed directions for brief periods of a rotation. But the beautiful image of a fractured landscape coordinating momentary eruptions collapsed under the weight of one simple observational fact. The jets of 3I Atlas were continuous. Not pulsed, not segmented, not dotted like pearls on a string. Continuous. If the jets truly flickered with each rotation activating only when the geometry allowed sunlight to enter a pit, then the material released would be naturally segmented in time. And because the gas takes a month to travel outward, those segments would appear in the jets themselves as spaced intervals, distinct puffs suspended along the length of each beam. Each pulse, separated by 16 hours, would form a repeating structure visible in the morphology of the trail. But no such structure existed. The jets were smooth, seamless, uninterrupted. Nothing in the images resembled discrete bursts of activity. There were no density fluctuations, no brightness modulations, no periodic thinning or thickening of material. The jets behaved as if they were not responding to cycles at all, neither diurnal nor rotational. They appeared to be anchored to a process that operated independent of the object's movement through space. This eliminated the terrain shadowing model decisively. The next theory aimed to preserve the possibility of natural behavior by invoking extreme collimation. Perhaps the jets were simply so narrow, so tightly directed, that rotation could not meaningfully distort them. Maybe 3I Atlas expelled gas through exceptionally small nozzles or vents, concentrating the outflow into beams of unusual precision. The narrower the source, the argument went, the more resistant the jets might be to the smearing effects of rotation. Yet, this explanation too crumbled when examined closely. Narrow jets do not ignore rotation, they respond even more visibly to it. A tightly focused jet from a rotating body produces dramatic spirals, the kind seen in rotating water jets, or spin-stabilized rocket exhausts in vacuum. Narrowness enhances curvature, it does not negate it, and the jets of 3I Atlas were not only narrow, they were flawless in their linearity. No curvature, no deviation, no trace of the rotational imprint expected from the underlying body. Another idea proposed that the object might have some form of internal structure capable of channeling gas in a fixed orientation, the natural equivalent of a rigid, hollow tube through which volatiles escape. Yet this too failed under scrutiny. Internal conduits cannot defy the external rotation of a rigid body. If the object spins, any channel embedded in its surface or interior would rotate with it. The direction of emission would still track the rotation, producing curves, not straight lines. The geology argument faltered further when scientists considered the necessary scale. To maintain a fixed jet direction over millions of kilometers, the orientation of the emitting region would need to be held stable to within a fraction of a degree. No natural surface terrain, no matter how deep or shielded, could provide that level of precision against the rotational momentum of the entire object. Rock does not hold direction independent of spin. Ice does not aim jets with astronomical accuracy. Topography does not override angular momentum. Every attempt to rescue natural explanations only highlighted the underlying problem. The jets were too perfect. Their straightness was not merely surprising, it was surgical, controlled, resistant to influence, resistant to the very rotation that defines the behavior of any natural comet nucleus. As the terrain shadowing theory collapsed, researchers turned to the breakup hypothesis. Perhaps the body had fragmented, and what looked like jets were actually linear debris trails. But observations from November 11th showed the nucleus intact, unbroken, structurally coherent. There were no companion fragments, no dust clouds, no signatures of disintegration. And debris trails would not maintain perfect linearity under solar radiation pressure. They would diffuse. They would broaden. They would not resemble collimated beams. So the breakup hypothesis dissolved as quickly as it was raised. The more scientists tried to impose natural structures onto the object, the more unnatural it appeared. The surface features required to produce pulsed jets were absent. The internal conduits required for directional stability were impossible. The geological shielding required to prevent rotational smearing contradicted the observed continuity of the jets. Nature seemed unable to provide a mechanism with the precision needed. Thus, the investigation reached a quiet but profound turning point. The jets behaved as if guided by an internal geometry that did not rotate with the rest of the body. This was the heart of the frozen physics problem. Not that the object violated physical laws, but that it behaved as if the laws applied in ways not seen in any natural comet. When the landscape model failed, it left a vacuum not in space but in theory, a void in which no natural explanation could stand without collapsing under its own contradictions. Into that void would soon enter a set of far more unsettling possibilities. Long before the jets of 3I Atlas forced physicists to confront their own models, the first cracks in the object's natural identity had already begun to form in the quiet chambers of laboratories, analyzing its reflected light. These early spectral signatures, barely noticed at first, contained ingredients that did not belong together, at least not in the proportions revealed. It was as if the object carried within it a chemical memory written in the unfamiliar dialect of another star system, a record of its formation preserved across eons of cold interstellar drift. What drew immediate attention was the nickel. Comets and asteroids both contain metals, but nickel is a shy element in the world of small solar system bodies. It hides in trace quantities, a whisper amid silicates and carbon-rich dust. Yet 3I Atlas exhibited a nickel abundance far exceeding any comet ever observed. It was not simply enriched, it was heavy with the metal, as though forged in a furnace where nickel was not a rarity but a rule. This single fact bent the expectations of origin. Nickel of such concentration suggests extreme thermal histories, violent stellar environments, catastrophic planetary collisions, or the remnants of differentiated bodies stripped bare by cosmic trauma. It implied that the object was old in a way our solar system objects are not old. Old in composition, in temperature, history, in metallicity. Whatever process shaped, it occurred under pressures and temperatures, unlike the gentle birthplaces of comets forming in the Kuiper belt or Oort cloud. It carried the signature of a different stellar parentage. Yet if the nickel told one story, the water content told another one even more jarring. Comets are supposed to be water-rich. Water ice is their essence, their archive, their currency of chemistry. They are frozen vaults of ancient volatiles, holding more water in certain cases than some moons. But 3I Atlas contained only about 4% water by mass. Not 40, not 20, 4. Such a low water fraction placed the object outside the taxonomy of traditional comets. It resembled neither the crystalline water composition of classical Oort objects, nor the dehydrated silicate-heavy mass of typical asteroids. It existed between categories, a stranger whose internal architecture defied the simple binary divisions astronomers rely on: icy or rocky, volatile, rich or volatile, poor, comet or asteroid. Instead, 3I Atlas behaved like something forged under conditions we cannot reproduce, a mixture of metals, depleted volatiles, and refractory minerals that had survived a long journey through radiation fields, cosmic dust storms, and the harsh emptiness between stars. It bore the signature of material older than the planets of the solar system, older perhaps than the Sun itself. Then came its polarization, the subtle twist in the orientation of light reflecting from its surface. Polarization measurements reveal surface texture, dust size, reflective structure, and scattering behavior. Every known comet produces a characteristic polarization curve, a predictable dance of angles and wavelengths. But the polarization of 3I Atlas was wrong, not slightly wrong, entirely wrong. It displayed a profile that matched no natural sample on record, neither cometary dust nor asteroid regolith. Something about its surface interacted with light in a way unfamiliar to astronomers, a scattering signature that suggested an unconventional texture or an unusual alignment of particles. When the data from the polarization filters were first published, researchers quietly admitted that nothing in their databases resembled the object. It behaved as though coated in material with optical properties rarely seen in small bodies, perhaps metallic grains aligned in patterns, perhaps mineral structures formed under exotic conditions. It was reflective in odd ways, absorbing and bending light differently depending on angle, producing glints and gradients that resisted classification. This was the point at which 3I Atlas began to feel ancient, not merely interstellar, but primordial. It carried the chemical afterglow of a long-lost environment. Like a shard chipped from a forgotten world, it bore witness to astrophysical conditions now washed away by time. Its dryness suggested a life lived in the heated depths of proximity to stars, or in the violent furnace of collision. Its metallicity suggested exposure to conditions too extreme for fragile ice to survive. Yet somehow, pockets of volatile material still clung to its shadowed recesses, dormant until awakened by sunlight near the Sunday. This conflict, an object both burned and frozen, made it feel paradoxically alive, like a survivor of cosmic trauma whose composition told stories of both fire and ice. But perhaps the strangest facet of its origin was not chemical at all. It was directional. The arrival path of 3I Atlas aligned uncannily close to the direction of the 1977 signal, a radio transmission of mysterious strength and clarity, never repeated nor fully explained. While astronomers cautioned that coincidence does not imply connection, the alignment was unsettling. The sky is vast. Arriving from the same region is statistically improbable, yet improbable things do occur. And when combined with the object's dozens of other anomalies, its nickel, its dryness, its polarization, its jets, the alignment became one more thread in a tapestry that refused to look natural. Scientists resisted the temptation to draw conclusions from direction alone, but they noted it, quietly, in private discussions and unpublished drafts. 3I Atlas did not behave like a body randomly flung from a disrupted star system. It traced a line through the darkness that suggested an origin with its own logic, its own vector, its own ancient history. As data accumulated, a portrait took shape not of a comet, not of an asteroid, but of a relic of conditions unknown, a shard of matter older than our models, formed under pressures alien to the cradle of the solar system. It was the beginning of a realization that would soon force scientists to confront questions not about jets or rotation, but about the nature of interstellar matter itself. What kind of cosmos produces an object like this? And what journey could shape it into what it had become? For months, the composition, rotation, and geometry of 3I Atlas had been confounding enough. But as astronomers traced its trajectory through the star field, an older ghost stirred a resonance not in physics, but in memory. For the first time in decades, scientists found themselves speaking in careful, hesitant tones of the wow signal. The 977 signal was never meant to be more than an anomaly, a sharp, singular spike in radio intensity detected once and never again. It lasted 72 seconds, carried a narrow-band clarity that no natural source had ever reproduced, and came from a quiet region of sky near the constellation Sagittarius. The coordinates were approximate, the uncertainty wide. Yet the direction became a part of astronomical lore, whispered about by researchers and wrapped in the mythology of extraterrestrial possibility. And then, more than 40 years later, 3I Atlas arrived from that same patch of sky. Not precisely the same, not enough to declare causality, but close enough to stir an echo, close enough to awaken an old unease. The coincidence was unsettling, the kind of alignment that statistics allow but rarely encourage. Yet alone, it meant nothing. Space is large. An interstellar object could easily wander from any direction, and the WOW signal region was no more or less special than thousands of others. But 3I Atlas was no ordinary wanderer. Its composition defied every known family of comets. Its jets behaved as if sculpted by an invisible hand. Its rotation contradicted the physics it should obey. Its polarization sitting in a category of 1, the coincidence, in this context, became a shadow stretching across the data, not evidence, not implication, but a whisper of narrative. Astronomers did not claim a connection. They refused to. Science does not permit leaps based on geometry alone, but many privately admitted the discomfort. The alignment was not proof, but it was fuel, a silent suggestion that perhaps the object's path through the galaxy was not shaped by random scattering alone. Trajectory analysis added to this unease. Most interstellar visitors arrive with high velocities, kicked from their home systems by gravitational interactions, planetary collisions, or the slow evaporation of ancient orbits. They drift for millions of years, their paths shaped by chaos, their destinations arbitrary. Yet 3I Atlas traced a smooth, almost stately path, steady, unhurried, free from the erratic, peculiar velocity shifts expected of a body flung chaotically from a distant system. Its motion lacked the signature tremors of violent ejection. It carried instead the calm of an object set adrift, intentionally, or shaped by a stability rare among interstellar debris. If one imagined the galaxy as a sea, then most comets were driftwood, scattered by storm currents. But 3I Atlas resembled something more deliberate, something traveling with a direction, not simply a trajectory. The connection to the WOW signal was not physical, it was psychological, an archetype resurrected by coincidence. But the coincidence sat atop a mountain of anomalies, and together they formed the impression of a pattern. To understand why scientists found the alignment so unsettling, one must understand the history of pursuit surrounding interstellar signals. The WOW signal was a rupture in the silence of the cosmos, a moment when the universe seemed to speak. Though it never repeated, though it never revealed its nature, it lingered as a symbol of our unfulfilled desire for contact. It became a myth of observation, a reminder that the universe occasionally flickers with hints of something more. And now, from that same region, an object arrived, carrying chemical signatures unlike any natural body, producing jets that broke the rules of motion and orientation. Was it coincidence? Almost certainly. Was it meaningful? No one could say. But the human mind is shaped for pattern seeking, and scientists are no exception. They simply discipline their pattern recognition with caution. Yet even caution cannot erase intuition, and intuition, in the case of 3I Atlas, began to whisper that something about this visitor felt orchestrated not in the intentional sense, but in the sense that its anomalies aligned too formally to dismiss as trivial. For instance, The object brightened faster than any comet ever measured. Its reflectivity curve suggested a surface that responded to sunlight with an almost metallic sheen, as though coated in microstructures that enhanced scattering. Its thermal behavior defied typical models of ice sublimation. Its dryness suggested extreme age, perhaps billions of years adrift. Yet its jets behaved as if young, energetic, coherent, structured. This contradiction between ancient composition and youthful activity deepened the sense that 3I Atlas did not fit into any known evolutionary pathway. Natural bodies do not remain dry for eons, only to suddenly awaken with hyper-precise jets at the exact moment of solar approach. Something about its history, its formation, or its journey was atypical. And this is where the wow signal re-entered the conversation not as explanation, but as metaphor. A reminder that the universe holds chapters we have not yet read, that the signals we detect are fragments, and that sometimes the fragments align. Astronomers, cautious as ever, avoided drawing a thread between signal and object, but they acknowledged the strangeness. They confessed that the universe occasionally arranges coincidences with unsettling elegance. The arrival direction was another anomaly in a growing catalogue, one more unresolvable piece of the mosaic. 3I Atlas began to feel like an emissary of the unknown, not because of the wow signal itself, but because the object's composition, behavior, and geometry hinted at an origin story radically different from that of ordinary interstellar debris. Perhaps it was born in the heavy metallic core of a shattered super-Earth. Perhaps it was shaped by the debris fields of a dying star. Perhaps it crossed through regions of intense radiation that burned away its ice and forged its metallic crust. Or perhaps, as some dared to consider in quiet conversations, it belonged to a class of objects, not yet catalogued structures, born from processes we have not witnessed, shaped by physics we do not yet understand. The wow signal did not return, but something else had arrived from its direction, something tangible, something visible, something measurable. And in its silent, drifting presence, the universe seemed to hold its breath again. Light is often the first language through which an unknown object reveals itself. Before its mass can be measured, before its orbit is refined, before any chemical signature is coaxed from its spectrum, an interstellar visitor announces its nature through the simple act of reflecting the sunday. The photons that strike its surface return to us carrying encoded messages, subtle variations in color, angle, polarization, and intensity. And for 3I Atlas, those photons carried warnings long before the jets or rotation paradoxes became clear. They whispered of a surface that behaved unlike any comet, unlike any asteroid, unlike any small body catalogued across decades of astronomical study. The earliest hints came from photometric curves, those delicate sequences of brightness plotted against time. As sunlight scattered from the body, its reflectivity changed in ways that should have mapped the contours of its rotation and the asymmetries of its surface. Yet the object's brightness variation, though consistent enough to determine its 16.16-hour spin, showed a peculiar smoothness, lacking the chaotic dimming and brightening patterns typical of rough, ice-streaked comets. It reflected light with a calm precision, as though its surface possessed a uniformity rare among natural bodies shaped by fragmentation, impacts, and thermal evolution. But the real shock arrived when polarization measurements were performed. Light polarization, the orientation of light waves after they scatter, acts as a fingerprint for surface texture. Comets typically produce polarization curves that rise predictably with phase angle, their dust scattering sunlight in a characteristic pattern formed from micron-sized grains suspended above volatile rich surfaces. The curve is so reliable that astronomers use it to identify comets at distances too faint for detailed imaging. 3I Atlas refused to follow this rule. Its polarization curve diverged so sharply from known behavior that some researchers initially suspected instrument contamination. The reflected light oscillated with an unfamiliar rhythm, as though interacting with surfaces smoother or more regular than the chaotic dust layers coating comets. The angle dependence of the polarization did not match any known regolith type, nor any mixture of dust and ice particles tested in laboratory scattering experiments. It was not simply different, it was alien to the catalogue of optical behaviors accumulated from decades of observing solar system bodies. This anomaly hinted at one of the object's most profound contradictions. 3I Atlas looked too organized. Natural surfaces age into disorder. Comets, especially, develop fluffy layers of dust, porous shells, and irregular grains that scatter light chaotically. But 3I Atlas reflected light with a coherence that suggested some combination of metallic particles, fine-grained alignment, or mineral structures forged under extreme conditions, structures that resisted the randomization typical of small body evolution. Its reflectivity posed a second challenge. The object brightened faster than any comet recently observed, and its surface returned sunlight with a spectral profile that contradicted expectations for a volatile, depleted body. A surface rich in metals should appear darker, absorbing more radiation. A body with only 4% water content should not develop reflective outbursts so easily triggered by sunlight. Yet 3I Atlas behaved as though coated in a composite material, one capable of interacting with light in ways neither purely reflective nor absorptive. When astronomers compared its spectral slope, the gradient describing how brightness changes with wavelength, they encountered a shape that belonged to no established category. It resembled neither the red slopes of dusty comets, nor the neutral or blue slopes of metallic asteroids. Instead, it formed a hybrid signature, a spectral tension pointing toward a surface chemistry and texture that did not conform to any model used to interpret alien bodies. This optical strangeness became even more dramatic when combined with the jets. Comets normally exhibit light scattered from dust-laden plumes, which radiate outward in soft, expanding arcs. These clouds scatter sunlight through countless particles, producing broad halos that shift and pulse as the jets curve with rotation. But the jets of 3I Atlas reflected light differently. Their brightness profile remained remarkably uniform across distances where natural jets should diffuse. In images taken days apart, the intensity along the jets declined smoothly but not chaotically. There were no clumps, no expanding cones, no turbulence-driven variations. Instead, the jets behaved like illuminated streams, coherent, sharply defined, almost mechanical in their uniformity. They looked less like dust plumes and more like controlled emissions. The physics of scattering demanded an explanation, but none came easily. To maintain such consistent brightness, the particle sizes, ejection velocities, and density distribution within the jets would need to be astonishingly uniform. Natural sublimation cannot produce such precision, not over days, not over millions of kilometers, not from an object with a rotating, irregular surface. The jets acted as if the material was sorted, regulated, and directed. Even stranger were the reflectivity signatures derived from the jets themselves. Spectral analysis hinted that some of the reflected light was polarized in a way that suggested columnar alignment of particles, an arrangement almost unheard of in cometary outflow, where chaotic expansion should randomize orientation instantly. Instead, the jets retained a subtle alignment, as though the particles within them shared a directional symmetry imposed at the moment of ejection. This raised a chilling possibility. Something about the structure of the jets maintained order at scales where disorder should reign. Natural gas plumes disperse. They fragment. They expand. These jets did not. Their light signatures behaved as though shaped by constraints invisible to telescopes, constraints that preserved the coherence of the jets far beyond what physics predicts. Some researchers proposed exotic explanations: magnetized particles, electrically charged grains, or mineral inclusions capable of interacting with the sun's magnetic field. But none of these theories produced simulations that matched the observed straightness, uniformity, and polarization. The light from 3I Atlas was telling a story, but the story was not one of randomness. It was telling of alignment, of discipline, of structure. In a universe where natural objects are shaped by chaos, 3I Atlas seemed shaped by something else, something that preserved order over vast distances, something that left fingerprints not of chance but of consistency. As the optical anomalies accumulated, a quiet question began weaving through the halls of observatories and the back channels of research groups. What kind of object reflects light like this? It was not yet time to confront the most unsettling answers, but the light had already begun to guide humanity toward them. By the time the jets of 3I Atlas had forced physicists into a defensive posture, scrambling for explanations that evaporated beneath the weight of the data, the scientific community's focus shifted toward the only remaining lifeline: direct measurement. Light curves, rotational inferences, and geometric analyses had taken the mystery as far as they could. The next step was to dissect the object, not from afar, but through the fingerprints carried in the material it expelled into space. For this, astronomers turned their attention toward the instruments designed to probe the chemistry of the cosmos: spectrographs. Spectroscopy is the universe's confessional booth. Every atom, every molecule, every ion that absorbs or emits light does so at specific wavelengths, producing a pattern as unique as a voice. By spreading the incoming light like a prism unravels color, scientists can read these signatures and reveal the hidden structure of distant stars, tenuous atmospheres, or the faint plumes rising from icy worlds. And now they turned that power upon 3I Atlas. Time was limited. The object was slipping through its narrow window of observability. Earth's rotation, orbital mechanics, and the jet structure itself imposed constraints on when and how data could be captured. But in observatories across the world, preparations moved with an urgency that bordered on obsession. If the jets were natural, spectroscopy would reveal familiar fingerprints: water vapor, carbon dioxide, carbon monoxide, and the spectral lines of common dust volatiles. If the jets were something else, the spectra would betray it. The first task was to determine the velocity of the outflow. Scientists had estimated the travel time by measuring the length of the jets, but spectroscopic Doppler shifts would reveal the motion more precisely, allowing them to distinguish between the speeds typical of cometary sublimation and those expected from more exotic processes. The expectation was straightforward. Natural comet jets should show velocities ranging from a few hundred to roughly 1,400 kilometers per hour, depending on the level of solar heating and the composition of the released material. Yet even before the spectrographs delivered full results, a pattern emerged in the preliminary data. The jets' velocities appeared unusually consistent. Natural jets wobble, fluctuate, and pulse with thermal variations. But the early measurements from 3I Atlas suggested a tighter velocity distribution than any known sublimation-driven outflow. A kind of steadiness, as if the jets were tuned rather than triggered. This raised a deeper question. Was the material accelerating smoothly from the surface, or emerging at a specific, preconditioned velocity? Spectrographs could answer this by detecting line broadening, how much the spectral lines smear due to speed variations among the particles. For typical comets, broadening is significant. For 3I Atlas, the broadening was unexpectedly modest, hinting at a cohesion that natural gas escapes rarely maintain. But velocity was only the beginning. The central prize lay in composition, what the jets were made of. Every natural comet's jets contain water vapor as the dominant component, followed by CO2, CO, and various organic volatiles. These produce unmistakable emission lines, the cosmic equivalent of a signature etched in ultraviolet and infrared light. If 3I Atlas were simply a dry, nickel-rich interstellar comet, the jets might reveal unusual proportions, but they would still contain the expected molecular family. Yet the scientific world braced for the possibility that the jets would not match this template. If the composition showed a deficit of water consistent with the object's 4% water fraction, then scientists would need to explain how such a dry body could produce jets of the magnitude observed. If the jets contained exotic volatiles, the explanation might lie in chemistry shaped under alien stellar conditions. But if the jets displayed spectra inconsistent with sublimated ice entirely, if they showed metallic ions, plasma emissions, or high-energy chemical signatures, then natural explanations would face catastrophic failure. Multiple observatories aligned their instruments accordingly. High-resolution spectrographs in Chile, Hawaii, and the Canary Islands began targeting the brightest sections of the jets. Space-based instruments, free from atmospheric interference, prepared to measure faint ultraviolet absorption features that ground telescopes could never access. Some teams coordinated with particle detection instruments originally designed to monitor solar-wind interactions, repurposing them to catch charged dust or ionized gas in the path of the jet's expansion. This multi-instrument campaign formed the backbone of the ongoing investigation. Each measurement aimed to pierce the veil surrounding the object and offer clarity where mathematics and imaging had only deepened the mystery. The hope was that spectroscopy would build a bridge back to familiar physics, a chart of chemical lines that told a coherent story of volatiles awakening after centuries of interstellar cold. If water vapor appeared at expected wavelengths and intensities, scientists could at least cling to the foundation of cometary chemistry. If carbon monoxide emissions dominated, they could propose an interstellar origin with altered ice ratios. If organic compounds appeared, they could tie the object to chemical pathways known in star-forming regions. But there was also the fear, increasingly spoken aloud, that the jets might produce lines indicative of processes not driven by solar heating, that they might reveal molecular fragments inconsistent with thermal sublimation, that they might display high-energy transitions suggesting ionization or electrical acceleration, that they might contain components impossible for natural comet nuclei to produce at all. The need for ongoing testing grew worse. At the same time, another question haunted the analysis. Could internal structure influence the jets? If 3I Atlas possessed subsurface reservoirs with unusual geometries, long conduits, aligned mineral grains, or magnetically active layers, could they shape the jets into their flawless beams? Spectrographs could help test these ideas indirectly by searching for metallic ions or crystalline dust particles emitted in predictable ratios. Natural conduits would produce chaotic mixtures. Engineered, or at least highly structured channels might release material of striking uniformity. The scientific pressure intensified further as the object neared observational limits. Once its distance or solar angle shifted beyond available viewing windows, the mystery would be sealed until another interstellar object with similar properties appeared, perhaps decades from now, perhaps never. Thus, the spectrographic data became something more than a measurement. it became the decisive moment. If the jets matched natural comet gas, a new physics of interstellar ices might emerge, an extraordinary discovery in its own right. But if the spectra returned strange, if the lines appeared where none should exist, or if the velocities betrayed a mechanism incompatible with heating, then the implications would ripple far beyond comet science. Spectroscopy, poised between revelation and upheaval, became the last lens through which 3I Atlas could be understood before crossing the boundary into the unknown. And the universe, silent as always, waited to see what story the light would tell. As the spectroscopic campaigns intensified and observatories across the world began pouring data into shared repositories, a sobering realization swept through the teams studying 3I Atlas. Every natural explanation offered so far, every hypothesis painstakingly built to contain the object within the known boundaries of comet physics, was failing. Not slowly, not gracefully, but abruptly, like branches snapping under the weight of an unseen load. One by one, the models collapsed in the face of accumulated contradictions, until what remained was a space where classical science could not comfortably stand. The first casualty was the rotational slowdown hypothesis. When the jets were discovered to be impossibly straight, some theorized that perhaps 3I Atlas had dramatically reduced its spin since the 16.16-hour measurements taken months earlier. A slower rotation could, in theory, reduce the curvature expected in long-distance outgassing. But this line of reasoning fell apart upon closer inspection. Catastrophic events are needed to slow an object's spin by such a magnitude: collisions, fractures, or massive outgassing torques. Yet no such events had occurred. The nucleus appeared intact in every post-November image, exhibiting no debris, no dust fields, no structural scars. Rotation does not simply evaporate. Angular momentum does not quietly dissolve into silence. And all available observations indicated the object's spin remained stable, untouched by any force large enough to alter it. The second natural theory, the surface shadowing model, failed even more dramatically. Its premise was attractive. The idea that tall mountains or deep pits shielded volatile, rich pockets from sunlight, allowing jets to activate only during brief windows of rotational alignment. But this explanation required the jets to pulse on and off, creating discrete segments along their million-kilometer trajectories. Since each pulse would be separated by approximately 16 hours, the jets should appear as a chain of expansions and voids. Instead, the jets showed total continuity, smooth, uninterrupted brightness over distances that no pulsed emission could mimic. The surface shadowing model was elegant, but 3I Atlas was not. The third theory, that the jets were debris trails from a breakup, crumbled beneath the simplest observation of all. The object had not broken. The nucleus remained coherent, a single reflective body without fragmentation signatures. Moreover, debris trails, even under ideal conditions, do not remain narrow and linear. They spread as solar radiation pressure pulls smaller particles outward. They diffuse into broad fans, not razor-straight beams. And they certainly do not remain aligned for millions of kilometers, while an underlying body continues a stable rotation. With the obvious theories defeated, the scientific community turned to more desperate constructs. Some proposed that perhaps the jets were being shaped by magnetic fields generated within the object. But magnetic fields capable of collimating million-kilometer gas streams require internal dynamo processes and conductive material distributions that no small body could sustain. The scale was too large, the energy requirements too extreme. To maintain magnetic collimation over such distances would demand a core behaving not like rock or ice, but like machinery. Others suggested electrostatic effects, envisioning charged dust grains streaming along invisible field lines. Yet electrostatic jets diffuse rapidly. They do not remain coherent, nor do they maintain direction across weeks of travel, and they do not produce the kind of brightness consistency observed from 3I Atlas. At this stage, the failure of natural theories became a phenomenon unto itself. The more data accumulated, the more the object's behavior sharpened into a contradiction that could not be softened or bent. A comet cannot behave like this. An asteroid cannot behave like this. No natural interstellar object should behave like this. The physics of rotation alone was enough to dismiss most models. The laws that govern angular momentum are universal, extending from neutron stars to drifting dust grains. A rotating body imposes orientation changes on anything emitted from it. This is not a matter of temperature or composition, it is a matter of geometry. And 3I Atlas's jets ignored that geometry entirely. Even the idea of exotic interstellar ices chemistry sculpted by alien stars did not rescue the models. No hypothetical ice, no matter its melting point or molecular weight, could maintain a fixed global orientation relative to space, while the body beneath it rotated 45 times. This left scientists staring into a void, not a metaphysical void, but a scientific one, a place where the frameworks built across centuries no longer connected the points of data into a coherent whole. For some researchers, this was exhilarating, an invitation to imagine new physics. Perhaps angular momentum behaved differently under extreme interstellar conditions. Perhaps volatile layers preserved internal orientation through crystalline or quantum effects. Perhaps space held mechanisms that curved behavior in ways subtle and unseen. But even these cutting-edge speculations ran into walls. New physics does not solve contradictions unless it explains the mechanism behind them. And no proposed mechanism, no matter how bold, could maintain straight jets over a month of rotation without invoking some form of stabilization or control. Control. The word entered discussions reluctantly, almost apologetically. It was spoken not as a conclusion, but as an acknowledgement of what the data resembled. Straight jets, fixed orientation, smooth emission, stability across 45 rotations. These were not the hallmarks of passive behavior. They were the hallmarks of regulation, of a system responding to orientation, of a process maintaining alignment, of an output guided by an internal frame of reference. Yet, even as some entertained the idea, others pushed back, not out of denial, but out of responsibility. Science cannot leap to engineered explanations without exhausting every natural alternative. And so the community continued to search, to test, to propose, all while the data steadily dismantled each hypothesis in turn. By now, the collapse of natural theories formed a pattern, each failure pointing in the same direction. Whatever was happening on 3I Atlas was not accounted for by standard cometry processes. It was something else, rooted either in physics not yet known or in structures not yet imagined. And as the spectroscopic results approached, the scientific world held its breath, knowing that the next set of measurements would either offer salvation or force them to confront the question many still feared to articulate. If this is not natural, then what is it? Long before anyone dared voice it publicly, the idea had already begun to take root in the quiet spaces between conversations. The possibility that the jets of 3I Atlas were not jets at all, at least not in the natural sense. They did not resemble the chaotic fountains of sublimating ice, nor the diffuse curls produced by comets tumbling under sunlight. They behaved instead with a calm sense of direction, a discipline of orientation that mirrored systems humanity itself had engineered. Thrusters. It was not the brightness of the jets, nor their length, nor even their metallic composition that first hinted at this possibility. It was the unwavering orientation, the refusal to bend, the refusal to spiral, the refusal to acknowledge the rotation beneath them. In spacecraft engineering, thrusters must fire in coordination with an inertial reference frame, an external, stable direction that remains fixed even as the craft tumbles. This is accomplished through sensors, gyroscopes, and control systems that track orientation in three-dimensional space. A spacecraft can be rotating, drifting, even tumbling end over end, yet its thrusters will still point in the correct inertial direction because the system that controls them is not tied to the craft's immediate orientation. It is tied to the larger framework of space itself. This is exactly what the jets of 3I Atlas appeared to be doing. Their direction did not depend on the object's rotation. Instead, the jets maintained a global orientation, holding steady across 45 rotations, as if locked to a fixed coordinate in space rather than to a vent spiraling around a nucleus. If one replaced the word jet with exhaust, the behavior suddenly made sense. If one replaced sublimation with propulsion, the paradox dissolved. But of course, replacing words is easy. Replacing physics is not. No scientist rushed to embrace this idea. It sat at the far edges of permissible speculation, a thought whispered in the mind before being quickly swept aside by the weight of caution. And yet, it grew stronger with every failed hypothesis, every contradiction, every anomaly that bent toward intentionality. To consider propulsion is to consider purpose. And purpose is a heavy word in the scientific lexicon, one used sparingly, hesitantly, and only when all natural explanations have dissolved into dust. But propulsion provides more than a narrative. It provides a mechanism, a way for jets to maintain direction regardless of rotation, a way for outflow to be continuous rather than pulsed, a way for the object to respond to forces and maintain a coherent path across interstellar distance. Propulsion systems, whether chemical, ion-based, or based on more exotic principles, share a set of characteristics. 1. They produce controlled outflow, not random, not chaotic, but regulated, with consistent velocity profiles. 2. They maintain fixed orientation. Thrusters align with navigational intent, not with rotational geometry. 3. They operate intermittently or continuously depending on need. A spacecraft fires thrusters when correction is required, not at random thermal triggers. 4. They produce directional exhaust that remains coherent. Even across great distances, thruster exhaust maintains a remarkably stable axis of emission. These principles mapped disturbingly well onto the behavior of 3I Atlas. The jets displayed velocity coherence unusual for natural outgassing. Their brightness remained uniform in ways suggestive of regulated flow. Their direction remained constant across weeks of travel, ignoring rotational movement. And their sudden onset, not a gradual awakening, but a switch-like activation, fit more closely with controlled mechanisms than with sunlight-triggered sublimation. Still, the scientific mind hesitates at the precipice of such conclusions. The moment one invokes the language of engineering for a cosmic object, one is immediately confronted with implications that reach far beyond astrophysics. To call the jets thrusters is to ask who built them, or what system produced the object, or how such systems could survive billions of years in space. It is to question the scale of intelligence, technology, or natural processes that could produce such behavior. Thus, the navigation hypothesis emerged not as a conclusion, but as a contingency, a final framework waiting to be activated if and only if the spectroscopic data refused all natural interpretations. But before that moment, the hypothesis lived quietly, woven into back-channel chats, shared in careful late-night discussions at conferences, whispered in conversations where professional caution relaxed into intellectual honesty. Those who entertained the idea did so not because they wanted it to be true, but because they could not ignore the discipline displayed in the jets. They recognized that navigation leaves fingerprints: control, coherence, vector stability, and 3I Atlas bore those fingerprints with uncanny precision. Some theorists argued that if propulsion were involved, it need not indicate intent or intelligence. It could be a remnant system, an automated mechanism still functioning long after its creators vanished, or a natural process that coincidentally mimicked the behavior of thrusters in ways humans had not yet imagined. The universe is old, after all, older than human science, older than human imagination. Perhaps there existed processes unknown to physics, magnetic plasma interactions, exotic ices, or crystallographic structures that produced controlled jets without any guiding intelligence. But this explanation required new physics, not simply new chemistry, and in the absence of such physics, the behavior continued to resemble propulsion. A few researchers approached the problem differently. They wondered whether 3I Atlas was not a craft but a relic, a drifting artifact propelled by ancient systems still functioning at minimal capacity. Perhaps a derelict object, no longer active, but whose propulsion channels had become exposed as sublimation vents. If those channels were originally designed to orient emissions, then even weakened or intermittent outgassing might preserve the directional structure of their geometry. In this scenario, the object was neither alive nor navigated, but mechanically shaped its jets, a fossil memory of its internal architecture. Others, more cautious, searched for natural frameworks that could mimic this behavior. Could the object have formed through processes that produce inherently directional crystalline conduits? Could magnetized minerals align jets along stable axes? Could electromagnetic interactions produce collimations so extreme? Every model required leaps unsupported by data. Meanwhile, the jets continued to draw straight lines across the void. As the navigation hypothesis grew more refined, scientists began analyzing the jets as if they were engineered exhaust, testing their geometry, their brightness decay, their collimation length, and their velocity signatures for patterns familiar to propulsion modeling. To their unease, the jets behaved eerily close to low-thrust propulsion exhaust under vacuum conditions. They lacked turbulent signatures. They displayed consistent divergence angles. They maintained vector stability across large distances. It was not proof, not even evidence in the strict scientific sense, but it was resemblance. Resemblance that tightened with every new observation, every failed natural explanation, every photograph of a jet too straight to belong to a spinning object adrift in sunlight. And though no one dared declare that 3I Atlas was navigating, the data quietly assembled a portrait shaped by one unignorable truth. If one wanted to design an interstellar object capable of adjusting its course with minimal mass loss, its exhaust would look almost exactly like the jets of 3I Atlas. And this, more than anything else, left the scientific world contemplating possibilities it had never expected to confront. As the days of observation dwindled and 3I Atlas continued its silent drift through the inner solar system, the scientific world entered a state of collective anticipation, an uneasy equilibrium between hope and dread. The spectroscopic data, still in processing pipelines, held the promise of clarity. Yet increasingly, researchers questioned whether clarity was even possible within the boundaries of familiar physics. The object had arrayed its contradictions with too much precision, as if each anomaly waited patiently for the next to join it, forming a pattern not easily dismissed as coincidence. What the community awaited now was not merely data, but judgment information capable of tipping the balance between natural explanation and the unsettling alternative that hovered at the periphery of every discussion. The atmosphere in observatories, research centers, and remote conferencing sessions shifted into a kind of scientific suspense. Conversations grew quieter, more focused. Hypotheses became bolder in private, more restrained in public. Preprints were drafted, deleted, rewritten, shelved. Theories emerged in cautious whispers: unknown ices, quantum-aligned minerals, magnetic interactions unseen in any comet. Others leaned toward the engineering paradigm with an uncomfortable honesty. But all agreed on one point: the next measurements would decide everything. Central to this tension was the question of composition. If the jets contained water vapor and carbon dioxide at velocities compatible with solar heating, the mystery, while profound, could still be contained within the realm of exotic but natural processes. Perhaps interstellar ices behave differently under certain conditions. Perhaps ancient bodies store volatiles in layered architectures foreign to the solar system. It would be a revelation, certainly, but not an upheaval. But if the spectral measurements returned anomalous line intensities, unidentified elements, ionized states inconsistent with thermal sublimation, or accelerations incompatible with solar energy alone, then the interpretive landscape would shift irrevocably. Scientists were not simply preparing for data, they were preparing for paradigm change. One of the most significant questions involved mass. The jets of 3I Atlas projected material across millions of kilometers with a precision that implied either a highly efficient natural mechanism or a controlled one. Yet the nucleus itself was small, too small by standard models, to sustain such a prolonged and powerful outflow without significant spin alteration. If the object's rotation remained unchanged even after weeks of mass loss, it would indicate one of two disturbing possibilities. Either the jets expelled far less mass than their brightness suggested, or the mass was expelled in a manner that cancelled rotational torque, something natural jets do not do. This placed extraordinary weight on the upcoming velocity distributions derived from Doppler spectroscopy. Should the jets display narrow-line velocities consistent across all sampled regions, it would imply a controlled release akin to a regulated exhaust, not random sublimation. Should the lines display the expected chaotic spread, it would restore some hope for a natural origin. Another question hung just as heavily in the air: temperature. Natural comet jets exhibit specific thermal signatures. Sublimated gases cool predictably as they expand, producing temperature gradients that spectrographs can measure through emission line profiles. But if the jets of 3I Atlas displayed temperatures or excitation energies outside the range of sunlight-driven processes, it would mark a dramatic departure from cometary physics. In private correspondence, some researchers admitted fear, not fear of danger, but of implication. Data that contradicted natural models would force the scientific community to confront a path rarely walked: the possibility that interstellar space contains objects not sculpted by random formation processes alone. These implications weighed heavily on mission planners and instrumentation teams. Some even proposed emergency observation campaigns, arguing that the object might represent an opportunity too rare to ignore. A few suggested repointing space telescopes, altering schedules, or even redirecting future probes, knowing full well that such actions required resources and time the object might not grant. But amid this rising tension, the heart of the matter remained simple. Science awaited an answer. In the meantime, researchers refined every conceivable model. They analyzed the jet morphology pixel by pixel. They simulated possible internal structures, layered caverns, crystalline conduits, fissures aligned by improbable geological processes. They tried to build natural systems capable of producing collimated jets unaffected by rotation. Every simulation failed. Some collapsed immediately. Others survived only until more data arrived. But each failure sharpened the scientific intuition that they were approaching a boundary, a conceptual edge, where the known rules falter and the unknown stands waiting. A few theorists went so far as to model navigation scenarios. They attempted to determine how much thrust would be needed to maintain a stable trajectory across interstellar distances. Others calculated the power required to generate jets of the observed length. Though these discussions remained unofficial and unpublished, they grew more frequent as the object's behavior continued to defy rotational influence. Even the skeptics found themselves sketching diagrams, testing hypothetical thrust vectors, modeling torque compensation techniques. The most unsettling realization was this: if one assumes the jets are controlled, the entire behavior of 3I Atlas makes sense. Its stability, its directionality, its lack of rotational coupling, its sudden activation, its coherent brightness, its uniform velocity profile, its compositional anomalies, its uncanny alignment with past astronomical mysteries. Everything that strained natural interpretations aligned smoothly under the navigation hypothesis. This was not a conclusion, far from it. It was simply the first model that did not fracture under the weight of the observational data. And so the scientific community braced itself for the incoming spectroscopy. If the signatures were natural, the object would still remain extraordinary, an interstellar relic unlike anything previously observed. But if the signatures were strange, or inconsistent, or engineered in their precision, then humanity would be standing at the edge of a truth far older and deeper than any comet trail. A truth carried quietly across the galaxy, wrapped in the cold geometry of a drifting object. A truth science was about to face. In the final days of its observability, as 3I Atlas drifted outward and the nights began to reclaim it from human eyes, a stillness settled over the scientific community. Not the stillness of resignation, but the kind that precedes a revelation, quiet, expectant, almost reverent. The incoming data would soon define how this object would be remembered, as a strange comet from another star, or as something that challenged the scaffolding of the known universe. In that narrowing space between possibility and conclusion, humanity found itself staring into a mirror that reflected not only the object, but its own longing to understand. And now, as the observational window narrowed, the question sharpened into its simplest form: what, exactly, had come through our solar system? All the evidence pointed toward a boundary object, something perched atop the divide between natural and unnatural, between physics we know and physics we have yet to imagine. The jets refused to curve. The rotation refused to matter. Spectral lines hinted at cohesion where chaos should reign. Every anomaly circled back to a single, disquieting revelation. 3I Atlas was behaving as if the universe had given it a rulebook different from the one that governs asteroids, comets, dust, or even interstellar wanderers. Its contradictions did not scatter randomly. They clustered. They reinforced one another. They aligned in ways that formed a narrative, one that neither scientists nor instruments could ignore. The nickel-rich composition suggested a violent birth in a crucible of unimaginable heat. Its dryness hinted at an ancient journey spent baking in radiation fields where volatile molecules could not endure. Yet its jets acted young, vigorous, coherent, as if powered by something deeper than sunlight. Even its optical properties, the polarization, the smoothness of reflectivity, the disciplined scattering behavior, mirrored not a world carved by collisions and thermal erosion, but a surface shaped by conditions foreign to cometary evolution. It reflected light like an artifact, not a relic of randomness. These clues did not point toward certainty, only toward consequence. For if the jets were shaped by internal geometry rather than external rotation, then something inside the object possessed an orientation independent of the body's spin. And if that orientation was fixed across weeks, then whatever mechanism governed it had to maintain reference against an inertial frame. Nature can perform wonders, but it does not perform navigation. Yet the scientific world held fast to restraint. A single anomaly invites speculation. 12 aligned anomalies invite caution. But 12 anomalies, accompanied by coherent jet behavior, rotational defiance, unusual composition, unexpected reflectivity, and an unnerving arrival vector demand confrontation. The truth, whatever truth awaited, lay in the spectra, arriving from telescopes tuned to the jet's faint glow. Those line profiles, those velocity distributions, those subtle chemical fingerprints would determine whether the jets matched the breathable cadence of natural physics or the mechanical signature of controlled emission. The outcome would decide whether 3I Atlas belonged to the natural history of interstellar matter or to a category for which we have no vocabulary yet. Researchers waited with a quiet intensity rarely felt outside the unveiling of gravitational waves or the imaging of a black hole's shadow. They waited because the object demanded it, because the universe, through 3I Atlas, had posed a question so clear and so profound that humanity could not look away. Was this a piece of cosmic geology, sculpted by ancient stellar furnaces and altered by light years of drift? Or was it something shaped by physics not yet known, by processes not yet imagined, by principles that once activated could produce the very coherence seen in those impossible jets? As the final models were run, and as the spectral lines neared full interpretation, a quiet realization spread. Whether natural or engineered, whether comet or artifact, whether relic or mechanism, the object had already changed our understanding of what the universe permits. It had shown us that the cosmos still carries mysteries capable of humbling the sciences built across centuries, that our frameworks, strong though they are, can be bent by a single drifting visitor, that the galaxy is not a barren sea of predictable fragments, but a living archive of phenomena that can overturn our certainty in a moment's glance. 3I Atlas had reminded humanity that knowledge is provisional, discovery is unfinished, and the night sky still holds secrets powerful enough to reshape our understanding of existence. And, as the object receded into the cold, it left behind a question that will haunt every generation of astronomers who follow. If something in our sky behaves as though guided, what story is it trying to tell? And now, as we let the final light of 3I Atlas drift beyond our reach, we feel the edges of the mystery soften. The jets, once sharp as thought, fade gently into memory. The contradictions loosen their grip. The numbers settle back into quiet uncertainty. The night, for all its vastness, feels calm again, its heavy silence no longer a threat, but a presence that holds more comfort than fear. Imagine the object now, shrinking to a dim spark, its strange geometry dissolving into the star-woven darkness. Whatever it was, comet, relic, engine, or something older than language, it moves peacefully among the quiet interstellar winds, untouched by the urgency it stirred in us. The cosmos resumes its slow breathing. The questions grow quieter, not because they are answered, but because the mind grows still enough to rest beside them. In this gentle fading, we remember that the universe has room for mystery, that not every visitor must yield its secrets, that sometimes the most enduring gift is the question itself, lingering softly like a distant echo. The stars remain patient, the darkness remains kind, and somewhere out there, 3I Atlas continues its long journey, drifting farther from the sunlit stage where it briefly revealed its impossible grace. Whatever truth it carries will wait, and for now, we close our eyes, breathe deeply, and let the unknown cradle us as the night becomes quiet once more. Sweet dreams.